Hello, hello. Good evening, everyone. I'm Saurabh Chatterjee, a faculty member at the Department of Astronomy and Astrophysics. On behalf of TIFR, I welcome you all to the third Professor M.S. VARDYA Memorial Lecture. It is our honor to have Professor Alessandro Morbidelli among us, who will tell us the fascinating story of how planetary systems form and evolve. I request all of you to please settle down as quietly as possible and put your phones on silent, please. Before the exciting look back to the formation of planetary systems, including our own, begins, I request our director, Professor Chengalur, to please say a few words.
Thank you, Saurabh, and it's a real pleasure to welcome you all to this public talk at TIFR. Research at TIFR, as probably all of you know, covers a very diverse range of topics of physics, chemistry, biology, maths, computer science, and in many of these areas of research, we are often one of the few, if not the only institution in the country where such studies are being carried out. So we regard it as part of our mission to have a vibrant outreach program aimed at communicating to the public the excitement of doing cutting-edge science. TIFR's outreach program is not just one of the oldest in the country, but it's also probably one of the largest and the most varied. For example, at the location of our large radio telescope, the Giant Meter Wave Radio Telescope, we run annually what is probably one of the largest science day programs in the country, with tens of thousands of people attending. All of the centers in Bangalore and Hyderabad also have very active outreach programs. Here in Mumbai, we have Chai and Why series of public talks, which has run continuously for more than a decade, alternate Sundays at the Prithvi Theatre in Juhu, and otherwise at Ruparel College. And of course, we also have a very long tradition of hosting public talks here at the Homi Bhabha Auditorium. So please do check out our webpage and social media feeds for the details of upcoming events. Although TIFR's outreach program has been going on for several decades, the talk that we have today is part of a relatively new lecture series, the MS VARDYA Memorial Lecture Series. I'm extremely grateful to Rekha Côte for providing the generous endowment through which these series of public talks are funded. We're also very fortunate to have with us a very distinguished speaker, Professor Alessandro Morbidelli, and I'm sure that the topic that he is going to be speaking on shortly, largely about extrasolar planetary systems, will be of great interest to many. You'll shortly hear a more formal introduction of the speaker, but I would like to take this opportunity to thank him for accepting our invitation and for coming here for this visit. In addition to this talk, he's also spending some time at TIFR interacting with the faculty and the students at the astronomy department. I'd also like to take the opportunity to thank Ms. Côte for her very generous gift, without which none of this would have been possible. This kind of philanthropic support is very important for TIFR, not just in carrying our mission forward, but also in taking us along directions which we otherwise may not have been able to explore. So thank you again. With that, I stop. Welcome again.
Thank you, Professor Chengalur. I now request Professor Bhaswati Mukherjee, the chairperson of the Department of Astronomy and Astrophysics, to say a few words about Professor VARDYA and the Memorial Lecture Series.
Professor Chengalur, Director TIFR, Professor Morbidelli, our speaker this afternoon, Ms. Rekha Côte, and Mr. Rizwan Quetta, students, members of the audience. On behalf of the Department of Astronomy and Astrophysics, it is my pleasure and privilege to welcome you all to the third MS VARDYA Memorial Lecture. This lecture series has been instituted in the fond memory of Professor MS VARDYA, who, together with Professor SM Chitre, had established the Theoretical Astrophysics Group in TIFR in 1963. I express my deep gratitude to Ms. Rekha Quetta, daughter of Professor VARDYA, for the generous donation which has made the lecture series possible. The aim of the series is to bring prominent astrophysicists to TIFR, Mumbai, to promote current areas of research in astronomy and raise awareness regarding the same among the general public. The series began in 2024, and in the first two editions, we had lectures by Professor Irina van de Schuck, a renowned astrochemist, and Professor Sarbani Basu, a renowned solar physicist. This year, we are very happy to have Professor Alessandro Morbidelli, a renowned planetary scientist, as the speaker. Let me sketch briefly Professor VARDYA and his intellectual pursuits. Born in 1933, Professor MS VARDYA did his MSc from the Benaras Hindu University and PhD from Yale University, working on the envelopes and interiors of late-type stars. He subsequently was a postdoc in Berkeley before he joined TIFR as a faculty member. His research work primarily involved development of model stellar atmospheres for late-type stars, including opacity effects arising due to the presence of molecules and molecular ions, and later he also looked into data from observations. He was a pioneering molecular astrophysicist whose work probably has become more relevant in the later years as observations of molecules in astrophysical environments became possible with improved technology, and astrochemistry is a vibrant interdisciplinary subject. He, together with his student, Professor S.P. Tarafdar, organized on one of the first conferences in astrochemistry, the IAU Symposium 120 in Goa in 1985, more than 40 years from now. The summary of the proceedings of which said volumes about the impact of the conference at that time. The symposium covered almost all aspects of astrochemistry, from the early universe to comets and meteorites. You will see that meteorites form some important part of what Professor Morbidelli is going to speak about, except ionospheres and planetary atmospheres. Basic atomic and molecular physics, experimental and observational results, and theoretical calculations and modeling all were stressed. Professor VARDYA was highly regarded in the Indian astronomy community as well, and had a long stint as the editor of the Bulletin of the Astronomical Society of India during 1966 to 1973. So without further ado, I once again welcome you all to this lecture and thank you all for being here. And I pass the mic on to Saurav, who will introduce our speaker. Thank you, Professor Morbidelli, for being here. Thank you.
Thank you, Professor Mukherjee. I now request Ms. Rekha Quetta to please come and say a few words.
Thank you, and warm welcome to all of you at this, the third lecture in this series, which is in memory of my father, Professor MS VARDYA. I've grown up at the TIFR campus. I consider myself to be very privileged that, while growing up, we were just surrounded by so many scientists, and we were in an environment which really encouraged a love of science and learning, and it kind of seemed automatic to me at that time. It was only when I stepped into the outside world that I realized it's not like that everywhere. And I think through this lecture series, I would really hope that, we can inspire other, young people to really explore the world of astrophysics and science, and encourage them in their pursuit of the same, and encourage that curiosity and learning in the youth. I think that's something that my father would have really been happy to see, as he was always very passionate about deep scientific discovery and always encouraged learning, reading, and growing as an individual. I would really also just like to take this opportunity to thank the team at TIFR, the director, Professor Mukherjee, and my friend Arnab, who introduced me to all of them. And thank you so much for organizing such wonderful speakers. And big thank you, Professor Morbidelli, for accepting our invitation and coming here today to give this talk. Look forward to hearing you. Thank you so much.
Thank you, Ms. Kaita. It is a great pleasure to introduce our speaker today, Professor Alessandro Morbidelli, one of the world's leading scientists in planetary science and celestial mechanics. Someone who spends his days thinking about how entire planets move, collide, migrate, and occasionally behave in ways that would make even the most chaotic traffic intersection look well organized. Professor Morbidelli is internationally renowned for his groundbreaking work on the formation and dynamical evolution of planetary systems. His research has fundamentally shaped our understanding of how planets form, migrate, and interact over billions of years. In particular, his work on models of the early solar system, such as planetary migration and dynamical instabilities, has helped explain key features of the solar system we observe today. We observe the planetary systems today, but their properties have been shaped by a variety of physical processes over billions of years. His work helps us understand these processes and their consequences. In other words, while most of us struggle to organize our calendars for next week, Professor Morbidelli studies systems that organize themselves over billions of years, with planets and their building blocks as the moving pieces. Professor Morbidelli is the acting director of the Lagrange Laboratories, CNRS, and works at the Observatoire de la Côte d'Azur in Nice, and also a professor at Collège de France in Paris. Over the course of his career, Professor Morbidelli has authored hundreds of highly cited scientific papers and several important books on planetary formation and solar system evolution. He is the chief editor of the influential journal Icarus, dedicated to planetary science since 2021. He is a member of several prestigious and influential scientific academies, including the French Académie des Sciences, Académie Royale de Belgique, and headed the National Planetology Program at CNRS. His contributions have been recognized with numerous international honors, including the Ure Prize, and his ideas have played a central role in shaping modern theories about how planetary systems around the sun and other stars develop and evolve. So we are truly fortunate to have with us someone who helps us understand not only our own solar system, but also the astonishing diversity of planetary systems throughout the galaxy. Please join me in welcoming Professor Alessandro Morbidelli.
Thank you, Suraf, for the generous introduction. Thank you for the invitation. It's an honor to be here. It's an honor to be the third speaker in this distinguished series of lectures. Hope I will accomplish. So we will speak today about extrasolar planets and our own solar system. So the discovery of extrasolar planets is the revolution of the century, if not in astronomy, because we rival with gravitational waves, in planetary science for sure. But the idea that there are other planets around other stars is certainly not new. So I'm certainly not an expert, but I think that in your culture, you have this notion of Brahmandas, which are sort of parallel universe, if I understand well, more than extrasolar planets. But it's clearly that by culture, you immediately think about multiplicity, about diversity. And so the existence of extrasolar planets may not have come as a shock. But they come from another part of the world, and in the world that is dominated by monotheistic religions, things are totally different, because there we have one God, one elected people, one elected planet, which is the center of the universe. That's it. And so proving that there are planets elsewhere is something really significant. So even in the Western world, ideas started to change at the end of the Middle Ages, after the Copernican revolution already showed that the Earth is not the center of the universe because we turn around the sun. And in particular, in Europe, there is this mythical person, so this philosopher, former priest, Giordano Bruno, who at the end of the 16th century clearly spoke of stars as other suns. And if the stars are like the sun, and because the sun is surrounded by planets, all stars should be surrounded by planets. Well, in Europe, it was still an obscurantism going on, so it was a very dangerous idea to propose. And indeed, Giordano Bruno was condemned as an heretic and burned publicly in the middle of Rome. So it was really not the good time to propose such revolutionary ideas. But then the idea that stars are analog of suns and in principle planets should exist, of course, took over also in Europe. So this debate about are there other planets around the stars or not finally passed from the domain of philosophy or religion to the domain of science with the discovery of the first planet. That happened in 1995 by two Swiss astronomers curiously observing from France. And that really was a paradigm shift in the debate, and for a good reason. These two scientists got awarded the Nobel Prize in 2019. The planet they discovered was a planet which had more or less the mass of Jupiter around the star, 51 in the constellation of Pegasus, so that name. But immediately this first discovery showed something astonishing. There was something weird, because a planet like Jupiter in our solar system is far away, it's far from the star. Jupiter is 5 times more distant from the sun than Earth. And this planet is very close to its parent star. Its orbit, the radius of its orbit, it's only 1/10 of the radius of the orbit of Mercury. So 1/10 of the Sun-Mercury distance. And the existence of such a body was absolutely not expected. So this came as a surprise, and all the subsequent discoveries of extrasolar planets confirmed this surprise. And before I detail a little bit on this, let's give a brief look to the solar system. The solar system is a very well-structured system. We have 8 planets, and the planets are physically divided into categories, which are physically dynamically divided in the solar system. In the inner part of the solar system, so the closest to the sun, you have the 4 terrestrial planets. These are Mercury, Venus, Earth, and Mars, an increasing distance from the sun. And these are planets relatively small. The Earth is the biggest. Venus is very close in size to Earth. Mars and Mercury are significantly smaller. And they are rocky. We have an atmosphere. Venus has an atmosphere. But in terms of mass, the atmosphere is completely negligible. These planets are rock, solid rock. And further away, so starting from a distance of 5 times the Sun-Earth distance, we have the 4 giant planets, Jupiter, Saturn, Uranus, and Neptune, which are giants because they are, in terms of size, in terms of masses. Jupiter is 300 Earth masses, Saturn 100, and Uranus and Neptune 15, 17 Earth masses, but they're also physically different. They are not rocky, they're not solid like us. Most of their mass is made of gases, and these are the same gases of the sun that make the sun, so hydrogen and helium. Particularly for Jupiter and Saturn, really most of the mass is in gases. Uranus and Neptune are sort of a mixture, something like 5 Earth masses of gases and maybe 10 Earth masses of solids. But so hydrogen and helium are a predominant feature of these planets, and they are basically absent on the terrestrial planets. And so these planets are ranked, terrestrial planets close in, giant planets further out. Another characteristic of the solar system that you can see here is the coplanarity. All the planets are orbit the sun on the same plane. And this plane is more or less aligned with the equator of the sun. And the orbits of the planet are circles, basically, deviate from circles slightly, but really little. And because the law of physics are universal, before the discovery of any other extrasolar planet, it was generally expected that planetary systems exist, that all planetary systems look like ours, right? Because if the law of physics ended up in making a system which has such a clear structure, well, they will repeat elsewhere, forming planetary systems with the same structure. And so finding a Jupiter that is not here, but closer to the star than Mercury was a real shock. And as I said, this shock repeated over and over with the discovery of more planets. This diagram shows the planets known today for which we have a mass. We have measured the mass, so we have a mass, accurate mass estimate. So each dot is a planet discovered. And here it's plotted with respect to the distance from the star and the mass of the planet in Jovian masses. So to have a reference, I put the symbol of our own planet, so you can compare what we discover around other stars with respect to what is here. So these are Mercury, Venus, Earth, Mars, so small and relatively close to the star, and then the giant planets, Jupiter, Saturn, Uranus, and Neptune. In addition, these dots are colored, and the color shows the shape of the orbit. Blue means that the orbit is circular, the eccentricity is 0. And like those of the planets here, all our planets basically have circular orbits. But if you have a green color, it means that the orbit is elliptic and approaches the star and goes away from the sun, from the star at every orbit. And so what we plot here is just the mean of the distance. And when the dot is red, it means that the orbit is extreme, it's so eccentric to pass very close to the star at pericenter, very far from the star at apocenter. So what you see here is that planets cover a wide region of this diagram, but they're not uniformly distributed. Right? Immediately you see by eye that there are 3 dominant groups. There is this group, which is called the group of hot Jupiters. They are called the hot Jupiters because they have the same mass of Jupiter. You see, they are on the same line, but they are much closer to the star, much closer than Mercury is to the star. So they are strongly irradiated by the star. So these planets are physically hot. The temperature in the atmosphere can be thousands of degrees. So that's the name. And the first planet discovered by Major and Queloz is one of these because being the biggest and the closest to the star and in some sense the easiest to discover. The second group is still a group of planets which have a mass comparable with Jupiter, but it's further out. And so these planets are colder because the star is far away, so they receive less irradiation. I rather call them, some people call them cold Jupiters. I rather also insist on warm to underline that many of these planets are actually here at 1-2 astronomical units, so at a distance comparable to the Earth or Mars. So these are planetary objects as massive as Jupiter, but they are located where here we have the terrestrial planets, not where Jupiter is. And then some are further away, as far as Jupiter, and then there are fewer and fewer planets as we go away from the star. This is due to observational biases. It's harder to find a planet if it's far from the star, but biases can be modeled, and it seems to be real that the number of planets decays as we go away from the star. And then there is a third group of planets, the most populated one nowadays, and possibly the most interesting for us in terms of wondering if there is life in the universe. And these are the planets are called super Earths or mini Neptune because they have a mass in between the mass of the Earth and the mass of Neptune. And so from there, the name. Now we have we tend to call mini Neptunes those for which we observe that there is an atmosphere of hydrogen, like Neptune, and super Earths, those that seem not to have that atmosphere. And all these planets, as you can see, are relatively close to the star again, and they are typically interior to the orbit of Venus, and many even interior to the orbit of Mercury. So what we can conclude from the observation so far is that many stars, 50%, possibly even 70%, have planets that don't have their analog in our solar system, right? We don't have a hot Jupiter. We don't have a warm Jupiter. We don't have Jupiters on eccentric orbits. We don't have super Earths. So 50% of the stars have planets that we don't have. The other consideration you can draw from this diagram is that there are no stars with planets like ours. You see, there are no dots here close to the Earth, close to Venus, close to Mars, close to Uranus and Neptune, and so on. Only planets we see close to Jupiter. Okay, but this, we need to be careful, is an observational bias. With the techniques that we have, with the technology that we have today, we will not be able to observe an Earth around a star like the Sun with the distance comparable to the Sun-Earth distance away, because it's too low mass planet, too far out. And the same is true for Saturn, for Uranus, for Neptune. So the fact that we don't see dots where our planets are does not mean that they don't exist. We are not able to observe them yet. So the only planet of our solar system that we are able to observe around another star with the current technology is Jupiter. And so if we want to ask the question observationally, how rare is our solar system? Because the only planet that we can observe elsewhere is Jupiter, we need to simplify our question. It's too early to ask the question, how rare is our solar system? But we can ask the question, how rare or common is the pair Jupiter, Sun, Jupiter? Okay, how often in the galaxy we find a star like the Sun surrounded by a planet like Jupiter? And this question now can be answered observation. So that's right. So first of all, stars come in a variety of masses, temperatures, luminosities. So for instance, in a ball of 30 light years, there are 400 stars. And this is the distribution of their properties in terms of mass, colors, and luminosity. Our Sun is a G star, and G stars are only 10% of all the stars. Most of the stars have a small mass and are called M stars. Some stars are more massive than the Sun, but they are even more rare than the Sun. So only 10%, so about 40 stars in this ball of 30 light years is comparable to the Sun. The rest is a different kind of beast. Then we know from observations, taking into account observational biases, that stars have about a 10% probability to have a planet of the mass of Jupiter. And this is true for solar mass stars and also for stars of other masses if you don't go to the extremes. But of these Jupiter mass planets, many don't look like Jupiter at all. We have planets that are very close to the star, and planets that have very eccentric orbits. So this is an example, for instance, of the Jupiter mass planets found so far. So some are very close to the star, others are very eccentric, and our planet, our own Jupiter, instead has a wide circular orbit. And only 10% of all the Jovian mass planets found around other stars have an orbit that is similar to that of our own Jupiter. So then you take, you multiply these fractions, right? You multiply these probabilities. Only 10% of the stars are like the Sun. Only 10% of the Sun-like stars have a planet with a mass comparable to the mass of Jupiter. Only 10% of those have an orbit similar to that of Jupiter. You make the product, it's already 0.1%, 1 in 1,000. Okay, so just one star in 1,000 is like the Sun with a planet like Jupiter. And the solar system is much more complicated than just the Sun-Jupiter pair. Right? We have all the other planets, but we cannot say much. But of course, it's less probable than this. For instance, some observations seems to hint that only one star out of 10 doesn't have any planet closer to the star than Mercury. The solar system, of course, doesn't have any planet closer to the Sun than Mercury. So if this is true, then the solar system, just characterized by the Sun-Jupiter pair and the absence of planets inward of Mercury, has a probability to occur of 1 in 10,000. So the conclusion already with observation is that the solar system is rare. Certainly not unique, because we have plenty of stars in the galaxy, plenty of galaxies in the universe, but rare. And you need to visit many stars to really find the analog of the solar system. So this brings a natural question which now dominates this field of science, dominates planetary science. What is the origin of the diversity of planetary systems? So one could think that maybe the formation of planet is just the result of a random process, or a stochastic process, right? It's like throwing dice, and sometimes you form a kind of planet, sometimes you form another planet, a different kind of planet, and so on. I doubt it's really a fully stochastic process, because as we've seen before, the planets are not everywhere on the diagram. They tend to form clusters. So there are planets which are recurrent and kind of planets which sort of don't exist. So personally, I think rather that planet formation has to look like like a bifurcation tree. That means that there are some processes which are universal, common, because the law of physics are universal. But at some point, the system becomes very sensitive to what can happen. And then little accidents can happen, little fortuitous events can happen. And this induces a bifurcation in the evolution. All of a sudden, because something happened or doesn't happen, one system evolves in this way, the other evolves in the other way. And then there is another crucial phase in the evolution with another bifurcation point, and then you can form different systems. And so at the end, we have a finite number of archetypes of possible planetary systems, of which the solar system is just one of the archetypes, and others are possible, but not everything is possible. So if this is true, we need to understand a little bit how planets form and how, for instance, we can have these bifurcations. Why, in some case, one system takes one direction of evolution, and in other case, a different direction of evolution. And my goal here in this first part of the lecture is to give some examples without the pretension to be, of course, exhaustive. So to do this, let me remind briefly and very schematically how we think planets form. So we know that stars, when they form, they are surrounded by a disk of gas and dust. The existence of the disk was even predicted in the 18th century, but now it's routinely observed. Every young star has a disk of gas and dust around it. And what happens is that this dust moves in the disk, the dust moves relatively to the gas, and in this motion, under certain conditions, it is possible that the dust form clumps of dust. And these clumps of dust sometimes become dense enough that the gravity of all these dust particles together keeps the dust particle bounded to each other. At that point, this dust cannot disperse in the disk anymore, has to contract, collapse on each other to form a solid macroscopic object that we call a planetesimal. Planetesimal is not yet a planet, is a solid body that has a size, say, of tens of kilometers, hundreds of kilometers. The asteroids or the comets that we have in the solar system are sort of planetesimals that remain in the system today and that for some reason have not been incorporated in the final 8 planets. So we have at the beginning the formation of planetesimals, not one, but many, of course. And then these planetesimals can interact with each other. They can collide with each other and so accrete and become bigger. They can also continuously accrete the dust in the disk. This process is called pebble accretion. And in this way, something went wrong. Because, no, but it's here. I don't think it's a presentation. I think it's a projector. There is no light in the projector. I see the presentation. I think it's also on Zoom. Yeah, it's also on Zoom. So it's not the Zoom line. It's not the computer. It's really the projector. Sorry. Came back. Okay. So All right, so where are we? Yes, so this these planetesimals can it's really weak. The planetesimals can collide with each other, can grow, they can keep accreting dust, that can grow, and they become so bigger, and so we call them protoplanets. And protoplanets can have various masses depending on how much mass is available, but let's think about objects the size of from the moon to something bigger. Okay. So indeed, how massive can be these protoplanets? Well, it depends on the material that is available. So in the disk, of course, the temperature is not the same everywhere. It's hotter closer to the star and colder far from the star. This is sort of obvious, which means that the elements that are solid in the disk are different, right? In the inner part of the disk, only the elements that can be solid at high temperature, what we call the refractory elements, can form dust. These are rocks, little grains of the rocks, like grains of sand. But there is a distance that we call the ice line, beyond which the temperature is low enough that water becomes solid, like ice. And so if you want to, when you form planetesimals and then protoplanets, if you are close enough to the star, you only have the sand at your disposal to build the planet. Whereas if you are far away, you, in addition to the sand, you also have the ice. And the ice has also nice properties because it tends to stick. And so you can form bigger dust, which makes planet formation more easy. And so the result of this is that the expectation that we have is that these protoplanets that form by the collisions of planetesimals by the capture of dust are relatively small in the region of the disk where you only have rocks at your disposal, you only have sand at your disposal, whereas it can be bigger in the region where you also have ice. And you can have a nice mass contrast of more than an order of magnitude. So these protoplanets are expected to have the mass of Mars, more or less, and these can have easily an Earth mass also. But now so at this point, all the systems should have the same structure, right? Because everything I said so far is rather universal. All stars have a disk, all disks are hot inside and cold outside. So all disks have ice at disposal to build planets only in the distant part. So all disks should build bigger planets outside and smaller planets inside. So where is the diversity coming from? There is one more universal law. And this universal law is that planets move. Once planets grow enough, they perturb the disk. And as a result of this perturbation, the orbit of the planet changes. It's what is called planet migration. The orbit, the planet moves radially in the disk, continuously orbit around the star, of course, but not as a closed orbit, as a spiral. And so it can approach the star. And the speed of migration depends on the planetary mass, which means that these small protoplanets tend to migrate more slowly, and these bigger protoplanets formed beyond the ice line tend to migrate faster. And that, what does it mean? It means that we enter into a phase of chaos because planets start to make a traffic jam, cross their own orbits, possibly collide with each other. So you have to expect something like this. Okay. And this is really the moment, so with migration, where a system that is initially born as an ordered system, all the systems the same, can become very chaotic, very, very complicated, and the part of the diversity, I think, stems from this process. And to show that this is not just a cartoon, I will show you a simulation done by Sean Raymond at the University of Bordeaux here. So what do we see? We see the star, we see the disk. Every time you see this triangle means that there is this protoplanetary disk of gas. And this is the distance from the star. You can imagine you are watching the system from the side, okay? You have many small planets and one major planet formed at the ice line. And I put here the Earth just as a symbol, just to remember that one astronomical unit is the distance at which the Earth is formed. And then, so this planet will migrate because it's massive, and this is what happens. So it migrates and destroys completely the rest of the disk. All of these small planets that were here in the region of the Earth have been wiped away. Some have been collected and pushed in and form other planets, others have been scattered, but there is no mass left at the location where the Earth would have formed if a bigger planet crosses in migration through this region. So migration is a phenomenon that can explain the diversity of what we see, at least partially. And so I will show that with 3 examples, again, without any pretensions to be exhaustive. So what happens in general is that, as I say, the major planets form beyond the ice line, only smaller planets formed inside where, for instance, the Earth is. And what happens is that these planets migrate towards the star. And they migrate, but they don't fall into the star because the disk is not extended to the star. There has an inner edge because there is a sort of cavity due to magnetic interaction. So the planets migrate until they reach the inner edge of the disk, and there they stop, they pile up together in certain configurations called resonances. And this configuration sometimes, if there are too many planets, can be unstable. So the planets interact with each other, they accrete with each other, they merge, so their number decreases, their mass increases, until you find a sort of stable configuration. And in this kind of evolution, so what you form is a system of super Earths, so planets that have multiple times the mass of the Earth. Here, actually, the colors indicate the mass of the planet. So you see orange, green, and red planets, so from masses from 3, 5, and 10-ish Earth masses, very close to the central star, at a distance of 1/10 of an astronomical unit, which is about a quarter of the distance between the Sun and Mercury. So this is a good, legitimate system of mini Neptunes that we see very often around other stars. But of course, our solar system is different, and not all stars have mini Neptunes close to the star. So what can happen differently? Could happen, for instance, that of all these planets that form beyond the ice line, one grows a little bit more, a little bit bigger, a little bit faster, enough to be able to start to capture the gas, part of the gas from the disk. And that increases its mass enormously and becomes a giant planet, like Jupiter. A giant planet also migrates towards the star, but more slowly. And so what happens in this case is that the giant planet migrates slowly over time. The time is here. The other smaller planets behind would like to migrate like those that we've seen in the previous animation and reach the inner edge of the disk, but they are behind the giant planet, and it's difficult to pass through the orbit of a giant planet. It's like when you are in a car behind a truck or a bus on a mountain road, right? It's difficult to overcome the bus or the truck, so you typically stay behind. And so at the end of the typical lifetime of the disk, 5 million years, what we have is that the giant planet migrated a little bit, but not too much. So it became a typical warm Jupiter between 1 and 2 AU. There are no super Earths close to the star, no super Earths at the inner edge of the disk. All the super Earths have been kept behind the planet. They exist, but they are behind the planet. They are far from the star. So this starts to look a little bit like our solar system in the sense that we don't have super Earths close to the sun. But of course, our Jupiter is not here. It's not where between Mars and the Earth. So in our solar system, what could have happened differently? Well, it happened that not only the innermost planet beyond the snow line accreted gas and became a giant planet, so became Jupiter, but also the second one accreted gas and became a giant planet, became Saturn. And simulations show that once you have Jupiter and Saturn together, they have some sort of gravitational game with each other that I will not try to explain, which basically blocks their migration. And so in this case, it's like before, but Jupiter and Saturn don't move. All these other planets would like to migrate to the inner edge of the disk, but now they don't have one track to overcome. They have 2 tracks to overcome. It's absolutely impossible. So they stay behind. They are blocked by the giant planets. And because initially they are many, they collide with each other. And at the end of this animation, if you are a little bit patient, these planets that are now 4 will finally merge and become 2 two planets with the masses of Uranus and Neptune. So actually this is the event. So we have two giant planets, Jupiter and Saturn, that remain far from the star, and the other planets eventually have merged together to form two planets of about 15 Earth masses, analog of Uranus and Neptune as in our solar system. But what is important, so we think this is more or less what happened in the solar system, but what is important is that in this game, as you can see, no planet came in the inner disk. So the inner disk remained a protected region, was not invaded by major planets like Uranus, Neptune, the precursor Jupiter or Saturn. And so the small protoplanets made of rocks that I described at the beginning, they are not wiped away, they remain there, and they have all the time to slowly build the terrestrial planets like Earth and Venus, which indeed built up on a time scale of about 50 million years. So if this is correct, we see that the structure of our solar system is due to two fortuitous events and that really sculpted the system. The first one, the first of this event is that of all these protoplanets growing beyond the snow line, one became massive enough to capture gas and become a giant planet, that's Jupiter. But the second fortuitous event is that Saturn also formed, blocking the migration of Jupiter. Without the first event, Uranus and Neptune or their precursors would have crossed the terrestrial planet region, removing the material from there, and the Earth would not have formed. And without the second event, Jupiter itself would have moved at the location of the Earth. And then, of course, the Earth could not have formed. But this is not all. We now have evidence that most planetary systems, after they form, once the disk is removed, become unstable. And the first evidence of this comes from the fact that, as I showed at the beginning, the warm Jupiters tend to have very eccentric orbits. But planets form in a disk, so they should all form on circular orbits. So if they form on circular orbits, why they are eccentric together? And well, the idea came actually first by my host, Saurabh Chatterjee here, but contemporaneously also by other groups, that the large eccentricity of the warm Jupiters that we see may be due to the fact that the planetary systems become unstable. And this animation shows what happens. So what we think is that when a star is able to form a giant planet, it forms several, at least 3. And then there are minor planets inward, closer to the star, where there are only rocks, and minor planets further away. When the gas disappears, so this triangle goes away, means there is no gas anymore, then the planets stay there for a while. The little planets try to accrete with each other to form terrestrial planets. But after some time, maybe some tens of millions of years, they become unstable. And when they become unstable, they cross their orbits, they have close encounters, and the result is that their orbits, which were initially circular, become eccentric. So now this planet has an orbit with an eccentricity oscillating between 20 and 40%. So something like the red orbit here. One of the planets has been sent far away, also in an eccentric orbit, and the third planet has been ejected into interstellar space, and it's now a rogue planet of the galaxy. Right? And in this instability, not only you generate large eccentricities in the orbits of the giant planets, but as you can see, all the little planets that were trying to make an Earth have disappeared. Right? The instability of the giant planets has destabilized the whole system, and all these little rocky planets have fallen onto the star or have been ejected, and there is no terrestrial planets formed. So we need to have been lucky again, right? We need to have been lucky that there has been no gigantic, violent instability in our system. Actually, we think that in our system, there was an instability of the giant planets. That's because in the way the planets form, as I showed before, Jupiter and Saturn don't migrate, and all the other protoplanets collide with each other to form Uranus and Neptune. At the end, we have a system of 4 giant planets like our own, but not at the location, on the orbits of our own. These systems are very compact. They are between 10 for Jupiter and 12 astronomical units for Neptune. But in the real system today, Uranus is at 20 astronomical units and Neptune is at 30 astronomical units. So what happened? So we think that there was a transformation in the planetary orbits. That when the disk went away, the planets that were surrounded by a disk of small bodies interacted with these small bodies and disturbed the small bodies, but they've been disturbed in turn. And this generated an instability. And in this instability, the planets also encountered with each other and separated from each other. And this dispersed the planetesimal disk, and in turn parked the Uranus and Neptune on their current orbits, circular at 20 and 30 AU, and left Jupiter and Saturn moderately excited, moderately eccentric, but not too much. In the case where, by chance, Jupiter and Saturn don't have a close encounter, very close encounter with each other. So this is the third fortuitous event that structured the solar system. There was a dynamical instability in our planetary system, as it generically happens every time you have giant planets. But in our case, by pure chance, it was a moderate instability that did not put Jupiter in particular on a very eccentric orbit. And that's why we are here, why the little rocky planets in the inner part of the disk have not been tossed into the star and could continuously collide until forming the Earth and Venus and the other terrestrial planets. So if all of this is true, then we understand that the solar system has to be rare, right? If you need 3 lucky events in concatenation, then of course this system, a system like ours, cannot be the most common system. Right? And but should, and we know from observations that this is probably true, but should from this conclude that life is rare? Maybe not. I mean, we should not do automatically this jump, because maybe it's not needed to have a planet exactly like the Earth in a system exactly like the solar system in order to develop and sustain life. And we may have life existing and thriving on planets which are different from our own, or planets that are similar to our own, but in systems which are different from our own. And so I would like, in the second part of this talk, discuss a little bit what are the prospects that life exists on more common planets than an Earth in a solar system. And the best candidate to host life, as far as we know today, are these planets that we call the super Earths. So let's speak a little bit more about the super Earths. The super Earths, as I said, are planets more massive than the Earth. Many are rocky because we measure both their mass and their size, and so we can measure their density, and they have the same density that Earth would have with their mass, so they have a composition similar to that of the Earth. They often come in systems, so in little planetary systems. And for instance, this diagram shows a system called Kepler-62 and compares it to the terrestrial planet system. So the plot is, the drawing is scaled correctly. So you see the size of the orbits compared to the size of the orbits of our planets. So this system is all inside the orbit of Venus. And you see the sizes of the planets compared to the sizes of our planets. So you see why they are called super Earths, because they are bigger than Earth. And this one is a sort of super Mars. And these orbits are also coplanar, quite coplanar and quite circular. So they really look like mini terrestrial planet system, just with the planets a little bit more scaled up. And they are, as I said, rocky. So maybe that's really what the most similar thing to Earth that we know of today. Of course, to host life, you need to have water. Biologists are categoric. Life cannot exist if you don't have liquid water, and there is no real other molecule that in chemistry, even in liquid form, that can perform the functions that water performs in the biological metabolism. And because we want to discover life, of course, we want that this water is on the surface, right? Because if the water is only in the subsurface, there may be life in the subsurface, but remotely we will never discover it. So if you want water on the surface, we need that the planet is at a good distance from the star. Because if the planet is too close to the star, it's incredibly hot and water evaporates. You cannot have an ocean, you cannot have lakes and rivers. All the water evaporates, goes in the atmosphere. You have a very thick steam atmosphere, and then this atmosphere is progressively lost. And so you dissociate the water and you lose the oxygen, the hydrogen. It's the case, for instance, that happened to Venus in our solar system. But you don't want to be too far either, because if you are too far, the sun is very dim, so the luminosity you receive is weak, the temperature is very cold, and all the water freezes out. And that's the case of Mars, where the only water that we have is in the polar caps or in the shallow underground in the form of ice. So you need to be in the correct location. And of course, the Earth is in the correct location. We have what exactly is this location depends on the composition of the atmosphere, the famous greenhouse effect. So there is a band, and depending on the property of the planet can be a little bit further out, a little bit closer in. But there is no planet that can sustain liquid water if it is too close to the Earth, to the sun, to the star, or too far from the star. So this is called the habitable zone. The range of distances where a planet, provided that it has the correct atmosphere, can have liquid water on its surface. So the habitable zone is located at different distances depending on how bright is the star. Right? If the star is very bright, the habitable zone is far away. And if the star is weak, then the habitable zone is close to the star. It's like if you have a big fire and you want to be comfortable, and you go away from the fire. But if you have just a little stove and you want to be comfortable, you go very close to the stove. So the habitable zone in this diagram has the decreasing distance from the star with the decreasing mass and luminosity of the star. And this is pretty interesting because, as I showed, the super-Earths are typically close to the stars. And so the super-Earths that are around stars like the sun or more massive than the sun are clearly too hot. They cannot have liquid water on their surface. They cannot be habitable. But the super-Earths that orbit stars that have a low mass are exactly in the habitable zone. So we not only know super-Earths which are rocky, we also know super-Earths around dim stars which are in the habitable zone. And there are clear famous examples. So for instance, this system is called TRAPPIST-1, because it was discovered by Belgian colleagues, and TRAPPIST is the name of their best beers. And this system is a system of 7 planets around a star which is only 1/4 of the mass of the sun. So it's extremely weak. And this planet this system has 7 planets the size of the Earth. Actually, they're not even super-Earths. You can see the scale of the dots is about the same. The system is tiny, right? It's here to show it. It is being enlarged by a factor of 25. But in reality, it's very, very small, much smaller than the orbit of Mercury. But because the star is so weak, there are 3 planets which are in the habitable zone. Not 1, like in the solar system, 3. Okay. So, these planets exist. And even the closest star to the sun, which is Proxima Centauri, which is the small star of the triple Alpha Centauri system, has a super-Earth in the habitable zone. And this is just a star 4 light years away from us. Okay. So the super-Earths in habitable zone exist. They are numerous and they are even close to us. So these are really the best candidates to start searching life, for instance, at least at the current time. But we should be careful, right? Because being in the habitable zone is just a necessary condition. It's not a sufficient condition. There are many things that make these planets different from Earth and how the Earth works. For instance, if you have a planet in a habitable zone around a small star, as I said, it's very close to the star. And so there are strong tidal forces, and these planets always show the same face to the star, like the moon always shows the same face to us. So it's true that these planets are in the good location to have, on average, a good temperature. But in reality, one hemisphere, it's always noon, the other hemisphere, it's always night. Okay. So what is the actual temperature on that planet? Maybe there is an atmosphere, there are winds, strong winds that redistribute the energy, so overall the planet is temperate. maybe there are not such a thick atmosphere, there are not strong winds, and so the only region with a mild temperature is the region at the transition between the illuminated hemisphere and the dark hemisphere. We don't really know. Another big difference is that these small mass stars have a low luminosity, but in particular during the first period of their evolution, they are very nervous stars that have many flares in radiations like ultraviolet and X-rays, which are, for life as we know it on Earth, very, very bad. You know, why you don't have to take too many X-rays, right? You can develop cancer and so on. And so these planets that are in the habitable zone around low mass stars are continuously bombarded by this high energy radiation, and it's really unclear what the effect that could have on the biological evolution. Another important property is the composition, because you can be in the habitable zone, means that if you have water on the surface, the water would be liquid, but you need to have the water, because you could imagine to form a planet completely dry. But you also need not to have too much water. And I will explain why. So for instance, on the Earth, we have very little water. It's a blue planet. The water covers 3/4 of the surface, but it's just a shallow layer. And in mass, the total amount of water that we have on Earth is less than 0.02%. And at least half of it is on the surface as a liquid ocean. If you have a super Earth, also with some water, but not too much, less than 1% in mass, you expect that the super Earths look like the Earth. So you have the rocky part of the planet and the surface ocean on the surface. But if your super Earth has a lot of water, for instance, is one of these planets that formed beyond the snow line and migrated all the way in, then things change, because you have a huge amount of water of the order of many tens of percent, maybe even 50%. So you would have a super thick surface ocean, but then the pressure at the base of this ocean, it becomes so high that the water becomes solid, becomes ice. Right? There are two ways to make ice. One is to cool the water, like in the fridge, and this makes ice that has low density, that floats on the water, but you can also just compress the water, and this creates ice that is dense and so stays below the liquid layer. And this is bad for habitability, because water by itself is not enough for life. You need to bring minerals to the water. You need to bring nutrients to the water for the biological activity to thrive. And on the Earth, this happens because the water erodes the oceanic floor, and even more erodes the continent, in particular thanks to the tides which are exerted by our moon. But if you have a layer of ice separating the liquid water from the rocks, this erosion would not exist. And so basically you would have, yes, a surface ocean, but this ocean would be more or less sterilized. And this is not just an imagination of a scientist. We have a satellite of Jupiter called Ganymede, which has exactly the same structure. So this is a satellite of Jupiter, it's far away. So the ocean on the surface is frozen, so it's covered by a frozen layer. But below this frozen layer, there is a liquid ocean. But below the liquid ocean, there is a thick layer of ice that separates the liquid ocean from the rocky part of the satellite. And we know that by studying the gravitational field of the satellite. So we're pretty sure that this is true. So composition really matters. And you need to have the good composition to be habitable in the habitable zone. And last example, I think also the time scale of formation matters, because if you form a planet too quickly, it becomes massive in the disk of gas, and so it will capture a little bit of hydrogen and helium to surround itself by an atmosphere with rich in hydrogen and helium. And this is what we call the mini Neptunes. They exist, they are observed. So planets that have this atmosphere of hydrogen and helium. So hydrogen and helium are not particularly bad for life. And there can be, for instance, bacteria that consume hydrogen and to produce methane. But one thing is sure, this kind of atmosphere would never become oxygen rich, because as soon as oxygen is produced, then the oxygen would go in the atmosphere, combine with the hydrogen and make water. Okay, so these planets would never have an oxygen-rich atmosphere, and the life on Earth started anoxic, but then produced oxygen. And the moment the atmosphere became rich in oxygen, then life could make a big jump in evolution, in complexity, because all of a sudden you can have a different cellular metabolism and make organism much more complex. So the mini Neptunes with the atmosphere of hydrogen and helium may sustain life, but that will be an extremely simple form of life that doesn't enact cellular respiration. So, the conclusion of all of this is that most stars are surrounded by planets. Now we know that for sure. We also know that the solar system is not typical. It's less probably than 0.01% of the stars, because too many contingencies and lucky events are needed to form a solar system like ours. But it's certainly not needed that for life to have a planet like Earth in a planetary system like ours. And the super Earths close to low mass stars are, at least for the moment, the best candidate to be habitable. And as I showed, there is one just 4 light years away from us. But it's not sure that super Earths in the habitable zone are really suitable to sustain life, or at least complex forms of life that we may hope to detect. So where do we go from here? The roadmap is to understand better the super Earths close in the habitable zone. And for that, we have now a telescope, the James Webb Space Telescope, which is doing atmospheric spectroscopy. And then this will be complemented by another dedicated telescope produced by the European Space Agency, Ariel. And if I understand well, also India is planning to have its own telescope to probe the atmosphere of these planets, which will really tell us about the atmospheric properties, if there is only hydrogen or if there are gases more similar to those that compose the atmosphere of the Earth. This will allow us to understand if these super Earths in habitable zones are really habitable or not. Then if you want to look for planets like the Earth, so around a star like the Sun, further from the star, for the moment we don't know any because we cannot detect them. And the next step is to try to find them. And the European Space Agency will launch a dedicated telescope, Plato, which should be the first one to be able to detect Earth-sized planets in the habitable zone of solar-like stars, if they exist, because we don't know if they exist and how numerous they are. So maybe the satellite will not discover any. And then the last step, if these planets exist, will be to characterize them. And this requires to have direct images of these planets. This is requires another jump in technology, like the one that would be performed by the Habitable World Observatory, which is currently at study mostly by NASA. So at the end, we will know more, of course, but we may discover, that we should be aware that life could be rare. Maybe it's not, but maybe it's rare. And if it's rare, it doesn't mean it does not exist, because there are plenty of stars in the galaxy and plenty of galaxies in the universe. But if life is rare, statistically, it will be around a star which is distant from us. And if it's around a star which is distant from us, we will have a huge difficulty in detecting it, because everything, we can easily measure stuff when it's close to the Earth, and very difficult if it's very far away. So if life is rare, it's well be possible that we will never discover it, right? So this story will not necessarily have a happy end, like a Hollywood movie or a Bollywood movie. We might end up at the horizon 2050 to say, okay, we didn't find life, which would be an extraordinary result by itself, because it would mean that now we know that empirically that life is rare. Whatever, discover life or not discover life, we will know much more about life in the universe, and so our own position in this universe. So thank you very much. And if you have questions, I'm at your disposal.
Thanks for the lecture. On the scatter plot you showed of all the planets with mass and distance, could you, what, in your opinion, how much is this driven by selection effects? Because I would understand the farther you go, you're more likely to see only hot Jupiters or something, and then.
Yeah. So yeah, as I said, so this is what we observe so far, and so there are selective effects. So it's a fact that there are planets around other stars that don't exist here, and we can do statistics. 50% of the stars at least have planets that we don't have here. Okay. But then there are regions where we don't know any extrasolar planets, and they can exist, but simply we cannot see them. So that's why, I mean, I never said in this conference that planets of an Earth mass at 1 AU don't exist or are rare. I don't know. What I think it's clear is that the whole architecture of the solar system is particularly rare because you need basically to prevent migration and prevent strong instabilities. And this is a low probability to occur. So I would expect that most of the systems are scrambled up. But maybe, you can have planets that migrate, and the last of the planets migrated less and stopped at 1 AU, and it's a water-rich planet that is fine at 1 AU, or you can have systems maybe without giant planets that somehow only form the rocky planets. I don't know if this is sure. So we don't know, right? In theory, we produce different planetary systems in the various simulations. So we typically aim to produce the planetary systems we observe, but sometimes the simulations go wrong and produce planetary systems which are different. So we also look at what kind of planetary systems we produce that cannot be detected currently. And certainly there are other possibilities to make terrestrial-like planets at the good distance.
Hello. Are there stars with hundreds of planets or thousands of planets? Or
No, no. I mean, the star that has the largest number of planets has 8. Okay, I think 8. If I'm not wrong, but that order. Okay, less than 10. And now, as your colleague said, you always have to wonder, what do you observe, right? What is the selection effect? So when you observe 1, 2 planets, 3 planets, it doesn't mean that there are no more, simply that you have not been able to see more. And then also depends which mass you define a planet, right? So the 8 planets found around Kepler-11, they are all pretty big, but maybe there are additional planets that have the size of Mars or the size of the Moon, so we don't know. But having hundreds of planets or thousands of planets, I think it's difficult, because when planetary systems are crowded, they are unstable. And so when they are unstable, the planets collide with each other until they become less numerous and more massive. And so by successive collisions, you simplify your systems to have fewer bigger planets until you find a stable system, and that remains for the age of the star. So yeah, we can have system with a dozen of planets, but I doubt much, I doubt more.
Thank you so much for the talk. You'd mentioned the TRAPPIST system. I was just wondering, because the planets have such high mass and they're so close together, would their gravities influence each other's orbits?
I'm not sure I got the question, sorry. Can you repeat?
Yeah, because in the TRAPPIST system,
Yeah.
since the planets are high mass and they're very close together,
Yes.
would their gravities affect each other's orbits?
Okay, sure. So yes. Yes, but the planets have the same mass of the Earth, but they are around a less massive star, and they are so in relative terms they are more massive than the Earth compared to the star, and they are closer to each other. So yes, they influence each other, and indeed we measure their mutual perturbations because their orbital period changes, because their orbit oscillates. But the TRAPPIST system remains stable, and it has been simulated, and it's a stable system. And it's also an old system, so as a system that has been there for billions of years. The star is not very young, so it's a stable system.
Thank you.
Thank you, sir. I have a question. Does the binary star, like a binary star system, does it affect the planetary dynamics, or is it the same for a binary star system with planets around it?
Yes, yes, that's a very good question, which I didn't speak at all about binary stars, and because our sun is single, but they exist. So many stars are binary, and we know that there are planets in binary systems. So typically, if the two stars are close to each other, the planets are around the binary, and if these binary stars are well separated, the planets are around one of the stars. So for instance, I gave the example of the Proxima Centauri b. So Proxima Centauri is a small star in a triple system, but the planet is very close to this little star. And so the other stars are far away, are weak perturbations of the system. So they can exist, and they do exist. In terms of formation, it's tricky, because we need to worry about the evolution of the disks and so on. And also these binary systems tend to change during the early phases of the early life of the star, because the stars are born in a cluster, so they feel also the perturbation of the other stars. So it's not so easy to understand how planets form. So for instance, there is a case, it's called Gamma Cephei. It's two stars that are relatively close to each other, but there is one planet around one star. And the problem is that in the current configuration of the two stars, if you put a protoplanetary disk around one of the stars, protoplanetary disk goes away very, very quickly. And so there is no time to form a planet, but the planet formed. So nobody knows how. And one of the ideas is that the two stars were more distant in the past, so there could be a well-developed disk that formed the planet, and then via the interaction with other stars, the binary became closer, but the planet already existed and could survive. But of course, we are not sure.
Amazing talk, sir. I have two questions. The first one is about the simulation that you showed us of the planets could out of the solar system.
This one with the instability.
Yes, with the instability one. Is it possible for those, what would happen to that planet which is going out of the orbit? Would it just be wandering in space, or does it get destroyed or something?
Okay, so here there are 3 planets. They have this big instability. So 2 remain in the system. One goes relatively close to the star on an eccentric orbit. The other one goes far, but remains around the star on an eccentric orbit. And the third is ejected. So this third planet leaves the star system, leaves the planetary system, and starts to wander in the galaxy like a star. Okay. These are what are called the rogue planets. So planets that travel in the galaxy, but do not orbit the star anymore. We think they exist because there is an observational technique which is called microlensing, which can detect them. It can detect objects because when they pass in front of a star by chance, because gravity bends the light, we see a lens effect, which magnifies the luminosity of the star that they occult. So typically you think something passes in front of the star, the luminosity of the star will decrease. And in that case, it's a gravitational lens effect. So the luminosity of the star actually increases, okay, seems to increase. And using this technique, a number of objects of a mass of the order of Jupiter, few Jupiter masses have been detected. So these objects don't have enough mass to be stars, because you need to be at least 13 Jupiter masses to be a star and have atomic fusion to produce energy, so be called a star. And so they are really planets, massive planets, and they go around the galaxy. More directly, we have discovered now 3 objects, interstellar objects, that passed through the solar system. Now, these are not planets, they are small objects, okay? Those were like comets. One was a few hundred meters, one was 2 kilometers, and the last one is about 1 kilometer, okay? So these are not planets at all, are planetesimals, okay? But also planetesimals during this rearrangement, instability of planetary systems can be ejected from the system. And so also planetesimals then wander around in the galaxy without turning around the star. And from time to time, they can cross another planetary system. And of course, planets are relatively rare, but planetesimals are billions and billions. And so this happens. And now that we have performant telescopes, in 5 years, we've discovered 3 passing through the solar system.
Sir, my second question is regarding the scatter plot. At around 0.01 Jupiter masses part, we can see some sort of a straight line perpendicular to the x-axis of the planets. 0.01 below that.
0.01, yes.
Yes, some sort of a distinct line. Is it just a coincidence, or is there any explanation for that?
So here, you mean you see a deficit of planets?
No, there is some sort of a, if you could get to a slide where the super Earth is not written, it would be much clearer.
Yeah, let me go to the other one. So it was at the very beginning, there was no... yeah. Yes, this one. I'm not sure. Again, you need to worry about observational biases. So this may be planets that are more easily detected, or for which we measure more easily the mass. And here it's more difficult to detect them or measure the mass, so they appear less numerous. So I'm not sure we see that. So there is a valley in the distribution of planets, but it's more visible when you plot a radius rather than mass. And this divides these mini Neptunes from the super Earths. So the mini Neptunes are larger. For comparable mass, the mini Neptunes are larger because they have this atmosphere of hydrogen and helium, and the super Earths don't have hydrogen and helium, so they are smaller. And so you see that there is a sort of dwarf dearth of planets in that valley. But in mass, I don't think that would be visible. So this, I think, is just an effect, an observational bias.
Thank you, sir.
Okay, I have a question here. So first of all, thank you very much for an outstanding presentation. Implicit in your argument for life or not, it was the presence of water. And is science now fairly clear that for some kind of life form, the hydrogen, oxygen, carbon combination is a requirement, and you couldn't really have anything, any meaningful other chemistries that could create the life forms? Is that a given now from a science perspective?
So first of all, I'm not a biologist. That's out of my comfort zone. But okay, I talk to biologists and so on. Biologists tend to be quite definitive in saying that the water is needed, because it's not just because it's liquid, but because the molecule of water is very polarized. And so it helps making a reaction, breaking molecules, recompose molecules, and so on. So for instance, having, you could imagine to have a colder planet that has a liquid carbon dioxide, but it seems much less favorable than developing life in liquid water. Then there is also this other question that, of course, when we talk about detecting life, we can hope to detect life if it's not too exotic compared to our own. Otherwise, you don't know what you would need to observe, right? Because ultimately, we will want to detect biomarkers in the atmosphere to say there is something. You will never image a planet with the resolution to see animals, right, or their constructions. So, but what you can hope to see are chemical compounds in the atmosphere that are abundant and should not be produced in such an abundance just by abiotic processes. And so for that, you want to have a life whose metabolism is similar enough to ours in order to understand what life can produce or not produce or consume. And so basically, if it's possible, if were possible to have completely exotic forms of lives, not based on carbon, not based on water and so on, who knows what they would consume and produce? And so we will never be able to detect them because we don't know what to search. Okay. So basically, in the search for life is implicitly a search for life whose metabolism is similar to the metabolism of life on Earth.
Thank you for your.
Thank you. Yeah, no, thank you firstly for that talk, which was really fascinating. My question also was on the second half of the talk. I remember there used to be these ideas that water on Earth came at late stages, perhaps from comets and things like that. I don't know whether that's still believed to be the case. But in any case, do things like this have consequences on the development of life?
Yeah, that's a very good question, because in principle, so if you want that a planet is in the habitable zone, in principle, in that zone, you don't have ice in the disk. So the water should be in gas form and you should not be able to accrete it. So there is a sort of paradox that to be habitable, a planet should be close enough to the star, but then in that case should not accrete any water. But of course, the Earth is a counterexample, accreted some water. So as you said, for decades, the idea was that Earth forms dry, but there are some planetesimals which are rich in water, like comets or a particular class of asteroids that formed beyond the snow line in the giant planet region. And as the giant planets form, they scatter these objects, and a fraction of these objects bombarded the Earth, deliver their material, deliver their water. And that's why we have just a little bit of water, not too much, but not zero. And that would argue that, you don't just need to form a planet, you need to form a full planetary system whose architecture must be such that you have enough mixing at some point in the system so that the water can come to the planet that is in the good location to host it then in liquid form. There has been a groundbreaking discovery in 2020 that showed that water can be synthesized on Earth by making hydrogen react with oxygen. Oxygen exists, it's in the silicate, right? And the question is, where is the hydrogen coming from? And in the case of the Earth, it does not come from an hydrogen atmosphere because the isotopic ratios are not good. But the discovery in 2020 is that the planetesimals that are the closest to thought to be the remnant of the building block of the Earth, which are called enstatite chondrites, have a significant amount of hydrogen bound to sulfur. Okay. And this hydrogen has the correct isotopic properties. And then once so delivered to the Earth, bound to sulfur, it can react with the oxygen in the silicate and synthesize water. And by doing some mass balance and so on, well, more or less, it's estimated that about half of the water on Earth comes that way, and half of the water has been delivered by collisions. From the astrochemical point of view, this is very important, because if water can be synthesized from the local blocks, then it becomes more generic that a planet in the good location will have some water. Whereas if the water on Earth had been entirely delivered by distant objects, then you need really to require that your global planetary system is such that you have this influx of distant objects. So in some sense, make the existence of water on habitable planets more generic than we thought before.
First of all, thank you so much for your knowledgeable lecture, sir. Sir, can there be any planet out of orbit and we can track?
I didn't understand. There was an echo, sorry. Try to speak lower, ask again.
Can there be any planet out of orbit? Just like he asked a correlated question, can there be any planet out of orbit? Just planets out of orbit jate hai na? It's related to that. Means, and what is super Earths? You are talking about super Earths, na? Our own planetary system.
Planets which are not in the orbital plane, which we have not detected in.
Okay. That's a good question. Well, we think we know our solar system, but in reality, there could be planets very far out that we have not detected yet. And actually, there are some ideas that a ninth planet could exist in the solar system, about 1,000 times the Earth-Sun distance. So the existence of this planet is not pure fantasy. It's because we have observed that the small bodies that go the furthest from the sun have orbits that are aligned with each other. And if this is true, you need that there is a massive object that forces all these orbits to stay aligned. And some calculation has shown that we need something like a planet of about 5-6 Earth masses, so a super Earth. We are on an orbit of about 1,000 astronomical units from the sun and an eccentricity of about 40%. The problem is that biases again, and we only know less than 10 objects that go so far. So it's true that their orbits are aligned within an angle, and statistically their alignment is significant, but because there are orbital biases, you are never sure that you have not observed the objects that are on different orbital orientation. So the debate is a scientific debate. It's non-conclusive, and we wait for more discoveries or a better characterization of orbital biases or detection biases, which will be possible with this new telescope that just started operating in Chile, which is called Vera Rubin. And then we will know if there is an anomaly in the distribution of small bodies that requires a distant planet or not. If this distant planet could exist in principle, because when you form Uranus and Neptune the way I described, like this, no, I will show it again. If you watch, no, it's this one. If you watch carefully of all these planets that tend to pile up behind Jupiter and Saturn and accrete to form Uranus and Neptune, a few are ejected. Okay, and so we go. Yep, for instance, one bloop, another one left. So these planets that are ejected could go in the interstellar space, as we discussed before, or if the sun was still in a cluster and the planet has been lucky, it could remain on a distant orbit, eccentric, inclined at about 1,000 AU from the sun. So it's not excluded that there are additional planets further out. And then if you go down in mass, like for instance, planets the mass of Mars, they could be in the Oort cloud, and we will never know about it. Right? So when the giant planets form, probably they form from a crowded system of planets and merge, and from the major planets we see, some are scattered away. So there could be smaller planets very far out.
Thank you.
Thank you for your talk, sir. It's really interesting. I have a very simple question. Is that like how our planetary systems have formed? Are we able to currently observe any solar system similar to ours in near light years, wherein we are in just that planetary system is just in the initial stages of maybe migration?
No, we are not yet able to observe a solar system like our own because, the Earth is small and its orbital period is long. So that means that the radial velocity signal on the star is too weak to be detected. The star, it's very unlikely that the Earth transits the sun from whoever is observing the sun because you need a perfect alignment. So it's very difficult to find planets like our own around other stars, and so that's why new instruments need to be developed. And in respect to migration, so in some, because our planets are relatively far away, yeah, in some sense they have to be able to avoid migration, right? And so in our solar system, there have been two ways to avoid migration. And for Jupiter and Saturn is their coexistence that really blocks migration. It's complicated, but it does. And for the terrestrial planets is that because there was not much mass in the inner disk, the planets were small at the beginning and they grew slowly. And so because planet migration is proportional to the planet mass, they could never migrate significantly because they were too small when there was the gas, and then the gas went away and the planets kept growing. So the Earth took about 50 million years to form, but the disk disappeared in 5 million years. And Mars formed in 5 million years. So the idea is that when the gas existed and the disk existed, the planets in the inner part were just the mass of Mars. And the mass of Mars, the migration is really slow. So you don't go anywhere. You don't go to the inner edge of the disk. If the Earth had formed in 5 million years, it would have migrated to the inner edge, but it didn't. It took 50 million years to form. We know that from radioactive chronometers. And probably took so long to form because there was not a huge amount of mass in the inner disk.
Thank you.
Let's thank Professor Morbidelli again. So there are refreshments outside. So please go outside and for more interactions and so on.
Thank you. Good level. Sure. No, in this